Welcome to Elevate Learn. In this comprehensive tutorial, we're diving deep into SQL subqueries and common table expressions, or CTEs. These are powerful techniques that will transform the way you write database queries. Whether you're preparing for interviews, optimizing legacy code, or tackling complex data analysis problems, understanding subqueries and CTEs is essential. By the end of this tutorial, you'll be able to write nested queries with confidence, understand when to use correlated subqueries, and leverage CTEs to create more readable, maintainable SQL code. Let's get started. Let's start with the fundamentals. A subquery is simply a query nested inside another query. Think of it as a query within a query. The inner query executes first, returning results that the outer query then uses. Subqueries are incredibly useful because they let you break down complex problems into smaller, more manageable pieces. They can appear in different parts of your SQL statement: the select clause, the from clause, the where clause, or the having clause. The key thing to remember is that subqueries must always be enclosed in parentheses. This helps the database engine understand the query structure and execute it properly. Subqueries can return a single value, multiple values, or even an entire table. Scalar subqueries are the simplest type of subquery. They return exactly one row with exactly one column, giving you a single value. This single value can be compared, assigned, or used in calculations. For example, imagine you want to find all employees earning more than the average salary. You can use a scalar subquery in the where clause to calculate the average salary first, then compare each employee's salary against it. Scalar subqueries are efficient and readable, making them perfect for situations where you need a single aggregated value. You can use them in select clauses to display calculated values alongside your main data, or in where clauses for comparisons. The database engine treats scalar subqueries much like it treats simple values, so performance is typically excellent. Beyond scalar subqueries, we have row and table subqueries. A row subquery returns one row but multiple columns, allowing you to compare multiple values simultaneously. This is powerful when you need to filter based on combinations of columns. A table subquery returns multiple rows and columns, essentially creating a temporary result set. When using table subqueries in the where clause, you typically use operators like in or not in. The in operator checks if any row in the subquery matches. The not in operator does the opposite. Table subqueries in the from clause create what's sometimes called a derived table or inline view. This is useful when you need to perform calculations on group data before using it in your main query. Notice how we alias the subquery as customer_orders, so we can reference its columns in the outer query. Now let's explore correlated subqueries, which are more advanced. A correlated subquery references columns from the outer query. This creates a dependency where the subquery needs data from the outer query to execute. Here's the key difference. The inner query executes once for each row processed by the outer query. In our first example, we're finding employees earning more than the average salary in their specific department. For each employee, the subquery calculates the average salary for that employee's department. The second example finds products with above-average prices within their category. Correlated subqueries are incredibly useful for row-by-row comparisons, but they can be slower on large datasets because the inner query runs multiple times. You'll often see them used with the exists operator to check for record existence. When performance matters, consider rewriting correlated subqueries as joins or CTEs, which we'll cover soon. Exists and not exists operators are specifically designed to check whether a subquery returns any rows. Unlike in, which checks for value matches, exists simply checks for existence. If the subquery returns even one row, exists evaluates to true. Not exists does the opposite, returning true when the subquery finds no matching rows. A best practice you'll see is using select one inside exists subqueries. The number itself doesn't matter, we're only checking if rows exist, not what data they contain. This makes queries more efficient. Exists is often faster than in when dealing with large result sets because the database can stop searching as soon as it finds a matching row. In our examples, we find customers who have orders using exists and customers without orders using not exists. These patterns are incredibly common in real-world SQL, especially when working with relational data. Let's shift gears and explore common table expressions, or CTEs. A CTE is essentially a named temporary result set that you define using the with clause. Think of it as creating a temporary named query that you can reference in your main query. The beauty of CTEs is readability. Instead of nesting multiple subqueries, you can break your logic into named, manageable pieces. The with clause defines one or more CTEs, each with its own name and query. Then your main select statement references these CTEs like regular tables. CTEs are scoped to a single statement, meaning they exist only for that query's execution. One of the most powerful features of CTEs is recursion. You can write recursive CTEs that reference themselves, perfect for hierarchical data or generating sequences. You can also chain multiple CTEs together, with each CTE potentially referencing previous ones. This makes CTEs incredibly flexible for complex data transformations. You can define multiple CTEs in a single with clause, separated by commas. This is where CTEs truly shine for complex queries. Each CTE is defined once and computed once. Then you can reference it multiple times in your main query or in subsequent CTEs. This is more efficient than repeating the same subquery multiple times. In our example, we define two CTEs. Sales underscore data calculates total quantities per product, and product underscore info filters products by category. Then our main query joins these two CTEs to get a comprehensive view. Notice the order matters. Later CTEs can reference earlier ones, but not vice versa. This allows you to build query logic incrementally, where each CTE builds upon the previous ones. When you have complex business logic involving multiple aggregations, filters, and joins, breaking it down into multiple CTEs makes your code much easier to understand and maintain. You can follow the logic from CTE to CTE, rather than parsing deeply nested subqueries. Recursive CTEs are advanced and powerful. A recursive CTE references itself, allowing you to traverse hierarchical or tree-structured data. They're essential when working with organizational hierarchies, category trees, or any data with parent-child relationships. A recursive CTE has two parts: the base case and the recursive case, separated by union or union all. The base case is your starting point. It defines the top level of your hierarchy. In our example, the base case selects employees with no manager. The recursive case then joins the CTE back to the original table, finding employees whose manager is in the previous level. This happens repeatedly until no more rows match. The level column tracks depth in the hierarchy. Recursive CTEs are incredibly useful but can be resource-intensive, especially with deep hierarchies. Always include a stop condition to prevent infinite loops. Most databases require the keyword recursive after with to use this feature. When working with recursive CTEs, test thoroughly with sample data to ensure your base and recursive cases work correctly. You might wonder, should I use a subquery or a CTE? The truth is, both approaches can achieve the same results. The choice often comes down to readability, maintainability, and specific requirements. Subqueries are fine for simple, single-level operations where the logic is straightforward. They work well when you need a quick, one-off calculation. However, when your query becomes complex with multiple levels of nesting, readability suffers. This is where CTEs excel. CTEs give meaningful names to intermediate result sets, making your code self-documenting. They're easier to debug because you can test each CTE independently. If you need to reference the same calculated result multiple times, CTEs compute it once and let you use it repeatedly, which can be more efficient. Recursive CTEs are another game changer. Subqueries cannot recurse. For complex data transformations involving hierarchies or sequences, recursive CTEs are your only option. In terms of performance, most modern databases optimize both similarly. Choose subqueries for simplicity, CTEs for complexity and clarity. Let's work through a practical real-world example. Imagine you're a data analyst preparing a sales report. You need monthly sales by region, and then calculate what percentage each month represents of the annual total. Using nested subqueries would be messy, but with CTEs it's clean and logical. First, we calculate monthly underscore sales, aggregating by month and region for the year 2024. Then we create region_summary to get annual totals by region. Finally, we join these CTEs and calculate the percentage that each month represents of the annual sales for its region. Notice how readable this is. Anyone reviewing your code can quickly understand the logic. If you needed to modify the calculation, you'd know exactly which CTE to adjust. You could easily add another CTE for year-over-year comparisons, or add filters for specific products or customer segments. This layered approach to building complex queries is exactly why CTEs are so powerful in real-world analytics work. Here's another real-world scenario: customer segmentation. Businesses often want to categorize customers into segments like VIP, regular, and occasional based on their spending. Then they want to see how each customer compares to their segment average. We start with customer_metrics, calculating key metrics, order count, lifetime value, and last order date for each customer. Then segment_stats creates segments based on lifetime value and calculates segment statistics. Finally, we join everything together to show each customer's lifetime value, their segment, and how they compare to the average customer in their segment. This type of analysis drives marketing strategies and customer retention efforts. You can identify VIP customers who are close to the regular threshold, regular customers at risk of dropping to occasional, and occasional customers you might target with promotions. These CTEs make it easy to maintain the analysis and adjust segment thresholds. If you change the VIP threshold from 500 to 7500, you only update the case statements. Performance matters in real-world SQL. While both subqueries and CTEs can produce the same results, how you structure them affects execution efficiency. Subqueries that appear in select clauses execute once per row of the outer query. If you have the same subquery multiple times, it calculates multiple times. CTEs, by contrast, are materialized once and cached for reuse. When you reference a CTE multiple times in your query, the database reuses the cached result rather than recalculating. Correlated subqueries are a particular concern. They execute once per outer row, which means massive performance degradation on large datasets. A table with 10,000 rows could cause your subquery to run 10,000 times. Rewriting as a join or CTE often provides dramatic improvements. For optimization, use explain or explain analyze to review your database's query execution plan. This shows how the database interprets your query and where bottlenecks might be. Index your columns, especially those used in subquery conditions and joins. Proper indexing can make the difference between a query that runs in milliseconds versus minutes. Let's discuss common mistakes that will save you hours of debugging. First, subqueries must always be enclosed in parentheses. Without them, you get syntax errors. Second, ensure your subquery returns the correct shape. If you're comparing a single column, your subquery should return one column, not multiple. Third, derived tables and CTEs should be aliased. Most databases require this. If you define a CTE, make sure you actually use it. And used CTEs are dead code. With recursive CTEs, always include a termination condition. Without one, you risk infinite loops or resource exhaustion. Fourth, use meaningful names. CTE_1, CTE_2 is terrible. Customer_monthly_sales. Regional_summary is clear. These names serve as documentation, making your SQL self-explanatory. Finally, test incrementally. If you're building a complex query, define one CTE, verify it works, then add the next. This makes debugging much easier than writing the entire query at once. When working with large datasets, test on a subset first to catch logic errors before processing millions of rows. Now it's time for hands-on practice. I've included several exercises to test your understanding. Exercise 1 asks you to find products priced above their category's average. This combines aggregation with filtering and is perfect for practicing basic CTEs. Exercise 2 is slightly more complex. Find customers whose spending exceeds the average for their region. Exercise 3 challenges you with hierarchical data. Build a 3-level employee structure showing managers, their direct reports, and those reports' direct reports using recursive CTEs. Exercise 4 involves RFM analysis, a classic marketing analytics approach that categorizes customers by recency, frequency, and monetary value. I've provided one solution here. Try all exercises before checking the answers. You'll find detailed solutions in the accompanying resources. The key to mastering subqueries and CTEs is practice. Start with simple queries and gradually increase complexity. Modify the examples from this tutorial to use different tables and conditions. If you get stuck, use Explain to review your execution plan. For advanced analysts, combining CTEs with window functions opens new possibilities. Window functions let you perform calculations across a set of rows while maintaining individual row-level detail. In our example, we use CTEs to calculate monthly sales by region, then apply window functions. Row_number assigns sequential numbers within each region, ranking months by revenue. Sum with partition by creates a running total of revenue within each region. These combinations are powerful for time series analysis, ranking, and comparative metrics. You might use rank or dense_rank for tied values, lag or lead to compare against previous or next periods, or tile to create quartiles or deciles. The CTE provides the aggregated data, and window functions analyze it further. This is exactly how professional analysts tackle complex business questions. You can track metrics over time, identify top performers, and perform sophisticated cohort analysis. Learning to combine CTEs, window functions, and sophisticated where conditions positions you as an advanced SQL analyst. While the core CTE syntax is similar across major databases, there are important variations. PostgreSQL and SQL Server support CTEs excellently, with full recursive CTE support and consistent syntax. MySQL added comprehensive CTE support in version 8.0, but older versions have limitations. Oracle also supports CTEs with the with clause. When working with recursive CTEs, note that PostgreSQL allows you to set recursion depth limits for safety. SQL Server uses offset and fetch for pagination, which pairs well with CTEs and window functions. Always check your database version documentation. What works in SQL Server 2019 might not work in 2012. Subquery syntax is more consistent across databases, which is one reason some teams prefer them for portability. However, modern database versions all support CTEs, so it's worth learning them. When writing SQL for deployment across multiple database systems, test thoroughly on each target platform. Tools like dbt and SQLfluff help manage database-specific SQL variations in production environments. While subqueries and CTEs are powerful, they're not always the best solution. Sometimes simpler is better. If you're just joining two tables with a straightforward relationship, a simple join is clearer and more efficient than wrapping it in a CTE. CTEs add overhead. You're creating and materializing a temporary dataset. For one-off, simple queries, this isn't worth it. Save CTEs for complex, multi-step analyses where they genuinely improve readability. Correlated subqueries on large datasets are performance killers. You're almost always better off rewriting them as joins with aggregation. The having clause accomplishes what the correlated subquery was doing, but much more efficiently. Another consideration: sometimes it's better to do calculations in your application layer. If you're loading data into Python, R, or JavaScript, complex transformations might be easier and more maintainable there. Not everything belongs in SQL. Choose the right tool for the job. Expert SQL developers know when to use advanced features and when to keep things simple. Over-engineering is a common beginner mistake. Your goal is clarity and maintainability, not showing off every advanced feature you know. Testing is crucial for reliable SQL. Here's the workflow I recommend. First, test each CTE in isolation. Run just that CTE's select statement without the main query. Verify it returns the expected number of rows and columns. Use count, aggregates, and group by to validate the data shape. Check for unexpected nulls that might indicate data quality issues. If a sum is null when you expected a number, investigate why. Second, add count and basic aggregates to understand your data. How many rows does each CTE return? What's the distribution of values? Are there outliers? Third, verify your join conditions carefully. A common bug is joining on the wrong columns or forgetting to join altogether. Use where conditions to sanity check your results. If you're joining customers to orders, every order should have a customer. Fourth, use limit when testing on large datasets. Run the query on the first 100 rows, verify the logic, then remove the limit. This prevents creating massive result sets that slow everything down. Finally, write tests in your CI/CD pipeline. If you're using dbt or similar tools, include data quality tests that verify row counts and key values. These automated tests catch regressions when source data changes. When you encounter SQL interview questions, here's the approach. First, clarify the requirement with the interviewer. If they say, find top customers, ask by what metric, in what time period, per region or overall. This shows you think critically. Second, start with the simplest solution. Get something working even if it's not optimal. Explain your logic as you code. Interviewers want to see your thought process. If you get stuck, talk through it. I need to aggregate revenue by customer and region, then rank within each region, then filter to top 3. Third, discuss trade-offs. A simple solution might use 3 separate queries that you join in the application layer versus a complex CTE-based solution. Both are valid. Understand the pros and cons. Finally, practice under time pressure. Many interviews give you 45 minutes for a complex problem. You need to work efficiently. Before the interview, practice writing queries quickly. Time yourself solving sample problems. Know your database's specific functions for date handling, string manipulation, and aggregates. Most importantly, communicate. If you're stuck, explain where you're stuck and ask for hints. Interviewers appreciate candidates who think out loud and collaborate. Let's recap what you've learned. Subqueries are queries within queries, useful for breaking down complex logic. They come in scalar, row, and table varieties, each serving different purposes. Correlated subqueries reference outer query columns and execute per row, powerful but potentially slow. CTEs, defined with the with clause, make complex queries more readable and maintainable. They're computed once and reused, making them efficient. Recursive CTEs handle hierarchical data perfectly. The key distinction: use subqueries for simple operations, CTEs for complex multi-step analysis. Your next steps: complete the practice exercises provided in the resources. Start with basic subquery exercises, then progress to multiple CTEs and recursive queries. Build projects using real datasets. Try analyzing open datasets from Kaggle or your local government. When you write SQL in your job, consciously choose between subqueries and CTEs. Refactor existing queries to improve readability. Most importantly, practice writing queries regularly. SQL mastery comes from repetition and exposure to different problem types. Join online SQL communities where you can see other solutions and ask questions. Consider certification exams if you want formal validation of your skills. You're now equipped to tackle advanced SQL challenges with confidence. Thank you for completing this tutorial on SQL subqueries and CTEs. You've covered foundational concepts, advanced techniques, real-world applications, and best practices. I've provided practice exercises, code examples, and a reference guide that you can download and use as you work with SQL. The resources section includes links to official documentation for PostgreSQL, MySQL, SQL Server, and Oracle, so you can dive deeper into your specific database. I encourage you to join SQL communities on Reddit, Stack Overflow, and dedicated forums. These communities are invaluable for getting help when you're stuck and seeing how experienced developers approach problems. Subscribe to Elevate Learn for more advanced SQL tutorials, including window functions, optimization techniques, and real-world data analysis projects. Don't just watch tutorials. Get your hands dirty. Write code. Make mistakes. Debug. Learn. The difference between watching someone code and coding yourself is enormous. Your growth as a SQL developer comes from practice. Start incorporating these techniques into your work immediately. When you encounter a problem, ask yourself, should I use a subquery or a CTE? The answer will come naturally over time. Thank you for learning with us, and happy querying.